So you've most likely heard that neurons send electrical signals, or that the inside of the cell is negative compared to the outside, but where does the voltage actually come from? Well, it isn't magic, and it isn't because cells contain a tiny battery. Instead, it emerges from the way ions are distributed across the cell membrane. For now, let's just focus on one ion, and in our case, that will be potassium. Okay, so imagine two compartments, both electrically neutral and separated by a thin semi-permeable membrane. We place a high concentration of potassium on the inside and a low concentration of it on the outside. So this difference in concentration will create a gradient. So potassium ions will naturally tend to diffuse out of the cell. If potassium were uncharged, that would be the end of the story. It would simply diffuse until the concentrations became equal. But it carries a positive charge, and that changes everything, because now every potassium that leaves the cell also carries a positive charge with it. So as ions move out, the inside of the cell becomes more negative, while the outside becomes more positive. That ion movement doesn't just reduce the concentration difference, it also creates a voltage across the membrane. So the concentration gradient pushes potassium out of the cell, while the electrical voltage pulls the positively charged ions back in. The Nernst potential is the membrane voltage at which these two forces exactly balance. At that voltage, there is no net movement of potassium, even though both forces are still present. Now that we have the intuition, let's look at the actual Nernst equation. In its general form, it looks like this. At first, this might look intimidating, but in physiology, we usually use a simplified version that works at body temperature around 37 degrees Celsius. So this is the version that you will usually use. Later in the video, we'll actually derive the full equation and show how it becomes this. But if your main goal is just to understand what the equation means and how to use it, this next part is the most important. So what does each part actually mean? E ion is the Nernst potential of that ion. Then we have the concentration ratio. It compares how much of the ion is outside the cell versus inside the cell. A useful way of remembering the ratio is the window analogy. So imagine you're standing inside a cell and looking outside through a window. So the concentration that you see on the outside goes on top, and the concentration you see on the inside goes on the bottom. Next we have Z, also known as the valence number or charge number of an ion. For example, potassium, which is K+, has a valence number of +1. The whole point of the equation is that it converts the concentration difference into a voltage. So now let's use the equation for potassium. Inside a cell, the potassium concentration is around 140 millimolar, while the concentration outside the cell is around 4 millimolar. Next, we have to determine Z. We know that potassium has a charge number of +1, so Z is equal to it. Now let's plug this into the equation. We get that the potential is approximately equal to -95 millivolts. So what does that tell us? It tells us that the two opposing forces will balance out when the membrane potential reaches -95 millivolts. Now let's see where the equation comes from. An ion sitting at the membrane is pulled into two directions, by the concentration gradient and by the electric field. So what we're really comparing are the two forms of energy, chemical potential energy and electrical potential energy. And at equilibrium, they cancel. The chemical potential energy for 1 mole of ions comes from the concentration gradient, and we can represent it as shown. R is the gas constant, T is temperature, and the logarithm appears because concentration gradients are not linear. Going from 1 to 10 is the same gradient strength as going from 10 to 100. Let's look at the electrical potential energy. This equation is for 1 mole of ions. Z is the valence, F is the Faraday's constant, and D is the voltage difference across the membrane. That last part is important. because E is not the voltage of either side, rather it is the difference in voltage between inside and outside. In other words, it's the membrane potential. Also important is that the electrical potential energy and the electrical potential are not the same thing. The energy depends on both the voltage and the charge, which is why Z appears in the equation. For example, a calcium ion with valence of 2 feels the same voltage twice as strongly as potassium with valence of 1. So, at the equilibrium, the two energies cancel out. So solving for E and flipping the ratio gives us the full Nernst equation. Now, to get the physiological versions, we have to convert temperature to Kelvin and plug in the gas and Faraday constant. Converting natural log to log base of 10 means multiplying by 2.3 and dividing by Z, and that gives us the final formula. So that's it for today, but in the next video, we'll go one step further. We'll explore the driving force, so what actually happens when the membrane potential is not equal to the Nernst potential. We'll also look at what happens when the membrane is permeable to multiple ions at once, because remember, the Nernst potential only gives us the equilibrium potential for one ion. Real cells are more complicated. Potassium, sodium, chloride, and other ions can all influence the membrane voltage. So next time, we'll ask ourselves, how do we calculate the actual membrane potential of a cell? Once we understand that, we'll actually derive the equation that lets us predict it.